All right, now what we want to do is look at parallel polarization. And once again, your author has made a similar error where he has flipped his y and z when talking about the plane of the wave, the coordinate system of the wave itself. So in this case, the H field is basically the one that has the perpendicular polarization, or that is perpendicular to the plane of incidence. And since when we discuss polarization, we always do it with respect to the electric field, then we call this parallel polarization because the electric field lies in the XZ plane. So his Y incident that he has labeled here actually should be Z incident, because once again we've taken the XZ plane and we've rotated it a total amount equal to the theta incident. And so E is called parallel because it is parallel to the plane of incidence. It lies in the plane. So going through the same deal we went through before where Y becomes Z, then we can get expressions for parallel and perpendicular, or for parallel reflection and transmission coefficients in terms of eta, the incident angle, and the transmitted angle. So um, once again, the end result is just fine. Just in the derivation, there was an error in coordinate system transformation. So, and since in the final result that has no bearing, then the parallel or the parallel reflection and transmission coefficients are perfectly fine. This is the interesting thing that I wanted to look at, because it turns out that in parallel polarization, there is actually an angle where we get zero reflection. In other words, the entire wave is transmitted. That angle is referred to as the Brewster angle. It occurs only in parallel polarization. You can see perpendicular polarization, the reflection coefficient with respect to the angle of incidence never reaches zero. Here we do have these zeros for different media. And so you can see that there is an angle at which we have zero reflection. The wave is fully transmitted. Sometimes that can be a useful way of eliminating parallel polarization and converting elliptical or circular polarization to strictly a perpendicular polarization by taking advantage of the fact that the Brewster angle eliminates all reflection. So that is the case then of the parallel polarization. You notice that they're quite different as far as their reflection coefficients, especially when it comes to this area around 60 to 80 degrees for most boundary materials. So the Brewster angle is an interesting angle. Um, the First thing to realize is that there is no such thing as a Brewster angle when we have non-magnetic materials for perpendicular polarization, but there is for parallel polarization. And so basically we can calculate the Brewster angle by taking the inverse sine of the following relationship, or the inverse tangent of epsilon 2 over epsilon 1 when the materials are non-magnetic and mu 1 is equal to mu 2. So it's interesting to talk about something referred to as the reflectivity and transmissivity of power. So here we're actually talking about the, the actual power density in the wave. Um, Waves do have to obey the law of conservation of power, and so you can actually look for power reflectivity and power transmissivity by looking at the power in the transmitted to incident wave and the power in transmitted to incident wave of perpendicular and parallel polarization. And so what you find is that basically they have the same relationship, this eta 1 cosine theta transmitted over eta 2 cosine theta incident. and then you have the transmission coefficient um, squared. So obviously it would be squared because it's power, and so it's proportional to the electric field squared. So this is just an idea of kind of the the amount of power um, that's transmitted for both parallel and perpendicular. So this is a very nice table, very useful. We have summarized reflection coefficient, transmission coefficient, the relationships between the two, the reflectivity, the transmissivity, these two refer to power, and the relationship between reflectivity and transmissivity, all summed up on this table for normal incidence, perpendicular polarization, and parallel polarization.